We still have one more example to run through. Step 03, so let's clean out our step 1 and step 3, and maybe this time, load up step 3 here. I'll ask for help from you guys on what I should do. And so we'll run step 3. And of course there's an error. So here it says, requested field is not available for output. It was in the fault cohesive dynamic. So let me review with you quickly what we're trying to do in this example. So if I go back to examples, so this is going to be a frictional interface, static friction, static simulation, static friction of 0.6, slip driven by simple shear. So it's going to try and cause slip on my fault by moving the boundaries and seeing what happens. So I'll catch up on our slides here. So this is getting back to marking the edges. This is a picture from yesterday reminding you that we do need to mark these edges of the fault, but we don't mark the edge when it gets to the surface. Here's the showing the figure with the purple region where I wanted the fault, and I had these extensions of one cell out. So I figured that. So there's my step 1. Here's my error message. Field type vertex data type data. So I'm in my vertex data fields. The available fields are slip rate, and traction. And the field that's not available is initial traction. So anyone have a suggestion on what I should do to fix this problem? Looks like Katie's going to volunteer. Oh, we got a couple people volunteering. Great. So Katie and Will are going to take a stab here. Okay, so let's look in step 03 where we have initial traction and switch it to traction. So let's replace initial traction with traction. Yep. So both Katie and Will suggested that we switch initial traction to traction. So let's see if we get any farther. Okay. So we have another error. Overly constraint point. Base C negative. So another degree of freedom 3, but number of tempted constraints is 4. So let me show you where our boundary conditions are. And I'll help you zoom in here. Any suggestions on what we might do to our .cfg files, to CFG file here to fix an overly constrained degree of freedom? My hint is that it's quite similar to what I had last time. So Farouk, I'm probably not pronouncing that correctly, says remove degree of freedom 2 from x negative and x positive. Because that's a vertical degree of freedom, and I've constrained the vertical degree of freedom on z negative. So that makes sense. So we'll constrain the lateral x and y on the lateral degree of freedom x positive, z x negative. Let's see if that gets us any farther. Okay, fault with label 605 on negative side of fault. So this is very similar to what I had before, where I have constrained a fault vertex. And I will let you know that I, in this case, want a through-going fault. So if I want the through-going fault, and I have constrained a vertex on the boundary, what should we do? So generally I can either make my fault not extend to the boundary, or I can remove it from the boundary.
So there's a hand up, Brad.
Obviously this works a little better if we're doing an in-person tutorial, but we appreciate you guys typing away. Remove 1 degree of freedom from the face on one slip, or remove the Dirichlet boundary condition. So let's see, what was our error message again? On the negative side of the fault, we have a fault vertex constrained. So I'll just let you know that the fault is in the parallel to the x face. So it's intersecting at the bottom of our domain. So we have a degree of freedom there. So we could either put that degree of freedom 2 back in the x displacements and remove our boundary condition on the z, or we can remove the fault from the z boundary condition, so z negative. So that's what I'm going to do. I'm going to remove that, and let's if that gets us farther. And it ran. So let's see what happened. And I'm just we haven't looked at the clearly I have not turned on any of the journal monitoring for this problem. So we don't see anything about diagnostic output. And so all we'll do is we'll just look at the debugging output. We're at step 03. So here's step 03. And let's see what the displacement field looks like. It looks a little funky. Let's warp it by a factor of 1,000. Let's with edges. Let's warp it a little more. Let's try 5,000. And so we gave it, so we deformed the boundaries. We moved the boundaries, sorry. And we're getting relatively non-uniform slip. It looks a little funky. Let's look at the fault. See what the fault looks like. So there's our fault. Let's see what fault tractions. Look at the color scale over here. They're sort of all over the place. What is our traction? That's magnitude. So there's our shear traction. Shear traction looks like it's essentially uniform. That one is a little ununiform. Normal traction. So there's, well, we have, I shouldn't say it looks, so our shear traction has positive and negative oscillations in it. So that's a very bad sign when it looks like, when we look at our warped image. Let's look at our Y displacements. Let's turn off the faults. What's our X displacement? X displacement. So we squished the fault. Give it a normal stress. So you can see our displacement over here on the left. We pushed it to the right. Our right boundary we pushed to the left. Our Y displacement. Looks like it was essentially 0. But yet we ended up with slip. And it's sort of all over the place. So it looks like we have a problem with our solution. So we better look at our convergence and see what was going on. And I didn't have any output, so let's turn on some monitors here. One of the things that we would want to show is whether I put in some max iterations, some tolerances. So let me look at the slides. I'm going to sort of cheat a little bit here. And so here are the settings that I want. So we'll just stick them back down here in the bottom. So what I'm going to do is I want to monitor my linear solution. I want to see, and it didn't copy over the underscores. I want to see if why my Petsy thinks my linear solution converged. I want to give an error if the solution did not converge. And the same thing with the SNES, the nonlinear solver. So with friction, I'm using the nonlinear solver because the deformation does depend. And I have a SNES monitor as well. So let's run that case. And so it diverged in the maximum number of iterations. So that's why I was getting a pretty funky solution. You'll see my linear residual was down to 10 to the minus 9, but and that's the preconditioned residual. But you'll see my SNES residual is at 1 times 10 to the minus 3. You'll notice that even my previous iteration is actually smaller, so my solution is actually diverging or oscillating around. You'll see here I was down to 2 to the minus 4 at the 100th iteration. But clearly it's not, you can see that it's not converging, it's not being reduced. So I'm doing something wrong. And let's go back to the slides to pick up sort of the next step. So I haven't converged. And so you can I'll often examine the residuals using a log file. So let me just show you how I often do that. If you spit too much to the screen, then you can't see. So let's capture everything to the log instead of just letting it go to the screen. And we'll grep for norm in step 03.log. That gives me all the norms. Let's do SNES function norm. So this shows me all of the SNES norms. And so I started out at 10 to the minus 1. I went down to 10 to the minus 3 by the second iteration, and I basically stayed there. So clearly, I've got a problem with the solution converging. So this is a friction problem. And so in friction, there are some special considerations that have to be included. This is specific to our fault implementation, that when we have to, because we're using an iterative solver, we have to be able to detect when the fault is stuck. And so what we do is we put in a tolerance for any displacements or slip values less than this are really assumed to be 0. So we have a 0 tolerance here. So we're going to add this 0 tolerance, and then we want to force our slip to be smaller than that tolerance. So that means that we really can't rely on the relative convergence tolerances and the KSP and SNES tolerances. We really need to force them to be an absolute convergence. So that's forcing our displacements and velocities to be less than that 0 tolerance. So here are some convergence tolerances. So let's stick those back. We'll stick those in the bottom of our .cfg file. So let's gotta clean this up a little bit from the cutting and pasting. This part of the discussion in terms of the specifics of fault friction we covered in last year's tutorial, June 2014. So if you want more information about fault friction, I strongly encourage you to go look at that tutorial. It's posted online. So we'll do a 0 tolerance of 10 to the minus 10. We'll make our linear solve tolerance smaller than that. So that forces the linear solve to if there really is displacement, it's going to be smaller than, or it's going to be bigger than 10 to the minus 12. If there really is 0, it's going to be smaller than 10 to the minus 12. And then our SNES relative tolerance, sorry, is 10 to the minus 20. And I think, did I have a SNES absolute tolerance? I did. SNES absolute tolerance of 10 to the minus 8. Yes. So I think I got the SNES KSP converge reason. Oh, I do. Thank you. So let's get back to running. So let's run again. We'll run it without the log file and see what happens. And what did I do? Missing an underscore in tolerance. And invalid literal for float. That looks right to me. So let's see what happened here. So it could be that my cutting and pasting. What do I want? Values that had some font issues here. Let's see what happens now. This did not convolve. So aha. Well, I was expecting that to work, but it didn't. I did not appear to get any further. Aha. So let's see here. So I ran into the same problem. And let's see what happens if I do that. So let's run it. And what I notice here is that I set tolerances in my step03.cfg file. And so those overwrite my settings in the PyLith app file. So we'll just nix those. One way, so I don't even get to the log summary to see what things are. I could, let's see. Let's turn on SNES view and KSP view equals true. Those would have told me, I believe. So let's see here. Absolute 10 to the minus 8 when I said I wanted 10 to the minus 12. So that was coming from here. So I would have seen those. So this is sort of the tricky part, is once we get into some of these more complicated physics, there is a you have to be careful, especially for the fault friction, very careful about solver tolerances. And so we strongly recommend that you look at the examples. And I really don't want to see those views anymore. So let's comment those out. But it looks like it ran. In this case, it converged in one SNES iteration, and with a tolerance now of 10 to the minus 12. So that means if it's one little iteration, we didn't need the nonlinear solve. So that generally tells us that the fault did not slip. So let's look at our deformed configuration here again. 5,000. Whoops. Maybe not 5,000. How about 100? Or 500? So there you can see we've squished our block together. Let's look at that displacement field. And there's a little bit of shear in there, but not much. So if we look at our fault tractions, let's look at fault tractions. So there's our X. Now our X traction is nice and smooth. Y traction, much, much less, essentially near zero, plus or minus very small value. Nice normal traction. So let's check our traction values. So let's take our shear traction, that's the first component, and take the absolute value of that. Oops. So absolute value, traction X, and divide it by the absolute value of traction Z. So we'll sort of not worry about the Y component. That's the up dip and num dip component. It's going to show the results. So what we see here is the result is our shear divided by our normal traction is varying from 0.38 down to 0.10. 0.10 at the ends where we have a free surface boundary, where our normal stresses are less. And 0.38 in the middle, we said our coefficient of friction was 0.6 when we set up the problem. So we don't have enough shear to create slip. So in this case, what we're going to do is we're going to increase our displacement. Let's go back to step 03. Where's our boundary conditions? So here's what I have. Let's see, what did I say I wanted? So I want -1 to 1 and 3 and -3. That looks like what I had, I thought. 3 meters, not 3 centimeters, I think is what I want. Is that what I want? Yes, 3 meters, not 3 centimeters. Okay, let's run again. Oh, we're getting some on there. It did take 70 iterations. This is a through-going fault, so this is one of the deficiencies of our current friction implementation, is that when you have a through-going fault, it does take a lot of iterations. But notice our number of linear solves per iteration is very small. We think we can do a lot better with our new fault implementation that we're implementing now. And so let's take a look. Oops. At what this looks like. deform it. We better do a factor of 500. We can do 1,000. Maybe I did 10,000 last time. That may have been my problem. So here's our displacement. Color it by y magnitude. There you can see our displacement along the faults according to shear. So we deformed our boundary. Let's load up the fault slip. Make sure it looks good. So let's turn off the domain. Let's color this by slip. There's our slip distribution. So at the edges, it's 0.7. In the middle, it's 1.7. If we look at our shear tractions, traction magnitude 1.5 to 1.7. So our shear traction, and that's the magnitude. So there's our x traction, basically 0.8 to 0.9. Our normal traction is minus 1.5 at the middle, minus 1.3 at the edges. Now if we do the calculator and do absolute value of traction x divided by absolute of traction z, what that is. Let's just call it, we'll just call it mu f, even though it's, because we expect to be basically equal to our coefficient of friction. And you'll see that except at the corners, that's where we have a little bit of in up dip, down dip direction. We're essentially right at 0.6. We can look over here in our little information tab and see that the values range from 0.585 to 0.6. So that's showing that yes, indeed, our shear tractions are corresponding to our coefficient of friction that we'd expected. And that's why we're getting slip everywhere. And so this was our successful friction problem. And so that sort of shows you some of the steps involved. In some of those cases, it was, our initial sort of errors were setting up the problem in the .cft files. But then it turned out to be sort of solver boundary condition issues to get what we really wanted. So there was sort of some back and forth in terms of setting up the solver parameters, diagnosing problems with the solver, and then making sure that we actually got the type of deformation that we wanted. So that wraps up those 3 debugging examples. We now have about half an hour left in this session that we can use to sort of talk about more general questions, if people have them, or additional debugging questions. We can switch back to the